The bell will probably ring during this, but these are the, this is kind of an explanation of what you did in the Vikings Villa lab and how it relates to electrons and what you'll be doing the next few days for electron configurations and that sort of thing. So the term electron configurations, first we have to have a definition of it. And all it really is how the electrons are distributed and how they are distributed among the orbitals of an atom. Okay, remember orbitals were S, P, D, and F. We talked about that in class. So basically it's saying where electrons are found and what energies they possess. So this is determined by distributing the electrons among the different sublevels and levels and orbitals. So among levels, sublevels, and orbitals. Sorry about the fitting in. I knew that would happen, but I thought I'd try anyway. Okay, so then there are 3 rules for writing electron configurations, and I think this is what you will recognize the most, that electrons are added one at a time, and they are added to the lowest energy orbitals until all electrons are accounted for. So that should sound familiar because that's what we did with our Vikings. We added them one at a time and we filled in the lowest floors first. So for a neutral atom, you have to remember that the number of electrons is equal to the atomic number, and therefore that is equal to the number of electrons that need to be accounted for. Okay, so each box on a electron configuration, and I'll show you the picture in a second, is considered to be an orbital. And the S sublevel is the lowest, then comes P, then D, then F is the highest. And sometimes they will overlap. So in terms of energy, when you get up to 4S and 3D, there's overlapping. So if we look at this picture, you can see the overlapping and as it occurs. And this should look very familiar to you. This is exactly your villa. And when we say overlapping, notice that there's a 3 here and a 4 here. So this is lower. This one is lower than this one, but that's just the overlapping and the change in energy. So keep going. So there are other rules. So we had Aufbau principle. Now we have Pauli exclusion principle, and you should know this. Orbitals hold a maximum of 2 electrons, and they must spin in opposite directions. Okay, Vikings don't want to poke each other's eyes out. To occupy the same orbital, they must spin in opposite directions. So we say that if there are 2 opposite spinning electrons, then they are paired. And if we have just a single electron, then we say that's unpaired. That's kind of obvious. So in order to write an orbital containing 2 electrons, this should be familiar to you from Vikings, we do arrow up and arrow down. Okay, and then each of those is an electron. So then the third rule, there's the bell, the third rule is Hund's rule. And what that says is that electrons occupy equal energy orbitals so that a maximum number of paired electrons results. So what happens then is that you place one electron per orbital until each has one electron, then you add a second. And again, this is just like in our Vikings villas. We add one per orbital and then add a second to the orbitals. Okay, so we wouldn't just have automatically filled them in from the beginning. So here is an example. Okay, so here are examples of orbital diagrams and sublevel notation. So we don't always draw out all of the squares that you can see on here. But rather what we will do is we will often just shorthand it so that it looks like this. And those are called electron configurations. So it's almost like a shorthand way of doing the different electron configurations. And so if there's one electron in the 1s sublevel, then what will happen is you will just put that as a superscript when you are writing the electron configuration. In sublevel notation is what we call that. So then we have, if you look at fluorine, you have 2, 4, 6, 8, 9. And then if you add up the electrons that are here, that does equal 9. So you're accounting for how many there are in the atomic number if it is a neutral atom. So let's do an example. Let's look at iron. And iron has 26 electrons. And so we would write it like this. The way that I generally have you do it is I put an Fe, which is the symbol, then I put 26, because that's how many electrons we have to work with. And then it's just a matter of adding the electrons. So 1s, 2, 2s, 2, 2p, 6, how many is that? 6, 7, 8, 9, 10. 3s2, 3p6, 4s2, and 3d6. Okay, you might be asking yourself, why do I have to memorize all of these in order? How will I memorize all these in order? Don't worry about that right now, because I'm going to show you an easy way to remember. But for right now, you can just refer to this image, this picture here. It's also in your textbook. But there's one thing I want to point out to you. So if we have 26 electrons, so we have 2, 4, 10, 12, 18, 26, okay? One last thing that we have to do is we have to look at how many are unpaired, okay? So we have the sublevel 3D, and there are 6 electrons. Now I want you to look down here to 3D. Okay, notice that there are 5 boxes, and I'm just going to draw them larger because this pen that I'm writing with makes it difficult. By the way, notice what I'm doing. I just merge the boxes together. I don't worry about drawing perfect boxes. So if we have, at the D sublevel, we have 6 electrons. So, and there are 5 orbitals. We would go 1, 2, 3, 4, 5, 6. So we add one to each orbital before we add a second one. So then the last part of this electron configuration, and the reason why I was showing you this, is because the last thing that you're going to write on here is you're going to write how many unshared electrons there are. And so, actually, I mean unpaired. Unshared comes later in the year. So the answer would be 1, 2, 3, 4. 4 unpaired. Now that's important later for bonding and that sort of thing and reactions, but I just wanted to show it to you now because then later on you can understand a little bit better the freeness of them, okay? So then the other thing that you might be asked to do, and this is on the bottom of your paper, okay, I'm just continuing along. You might be asked which element has a sublevel notation. And this is probably one of the easiest things because all you do is you add together all of the electrons. So 2 plus 2 is 4, plus 6 is 10, 12, 18, 28, 29, 30, plus 5 is 35. And so then we look on the periodic table, and right here, element number 35 is bromine, and so that would be the answer, bromine. Now, I said that there would be an easier way for you to remember the order of the sublevels, and this is how, using the periodic table. We use the periodic table for just about everything that we possibly can because it is the best guide and for so many reasons. And the reason why here is because the elements are grouped by type of orbital, and I will show you what that means. And it is into which electrons are placed. So the first S subshell is 1s, the first P is 2p, the first D is 3d, and the first F is 4f. Okay, now if you can remember this right here, and if you can remember which block is which I'll show you what that means in a minute, then you are going to be in great shape and you will be able to do electron configuration. So let's fill this in. We have all of these boxes here because I want to show you the sublevels. So what you're going to do is you're going to actually write, this is a 1s, this is a 1s, this is 2s, 3s, 4s, 5s, 6s, and 7s. Now, what we say then is that that is the S block. Notice the color coordination. Then the P block, and you skip over this whole middle. These are the transition metals, which we'll talk about more later, but they're just kind of odd. You skip over here to the green, and what did we say was the first P sublevel? 2P, 3P, 4P, 5P, 6P, okay? And then those are the P block. And then the transition metals, and I don't know why it doesn't have it on here, but is the D block. And what did we say was the first D? We said it was 3. 3D, 4D, 5D, 6D. And then last but not least are the F blocks. So we said it was 4F and 5F. And so remember yesterday in class I said, or well today I guess technically, in class I said that each box on the periodic table is considered to be one electron. So then what you're going to do is you go from left to right, top to bottom. 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Okay, and that's all you do is you follow the order all the way down. So you find which element you're interested in, and then you just trace from the very beginning what sublevels you go through, and that's how you write your electron configuration.